Now we'll learn about the join family of operators in SQL. Going to our select from where statement, in the from clause we list tables separated by commas, and that's implicitly a cross product of those tables. But it's also possible to have explicit join of tables, and this follows the relational algebra style of join. There's a few different types. One of them is what's called the inner join on a condition. And we'll see that that's equivalent to what in relational algebra we were calling the theta join, where the theta here is a condition. So it's effectively taking the cross product, but then applying a condition and only keeping the tuples in the cross product that satisfy the condition. The separate type of join we can use in SQL is the natural join, and that is in fact exactly the natural join in relational algebra, where it equates columns across tables of the same name. So it requires the values in those columns to be the same to keep the tuple in the cross product. And then it also eliminates the duplicate columns that are created. And we'll see this very clearly when we get to the demo. The third type of join operator in SQL is, again, the inner join, but with a special clause called using and listing attributes. And that's kind of, again, like the natural join, except you explicitly list the attributes that you want to be equated. And finally, the fourth type, and actually the most interesting type, is the outer join. And there's a left outer join, right outer join, and full outer join. And this is, again, combining tuples similar to the theta join, except when tuples don't match the theta condition, they're still added to the result and padded with null values. Now, I will say right off that none of these operators are actually adding expressive power to SQL. All of them can be expressed using other constructs, but they can be quite useful in formulating queries, and especially the outer join is fairly complicated to express without the outer join operator itself. So as usual, we'll be doing our demo with our simple college admissions database with college table, student table, and applied table. So let's move ahead to the demo. As usual, we'll have 4 colleges, a bunch of students, and students applying to colleges. Let's start with a simple query that we've seen before, which matches student names with majors to which they've applied. So that combines the student and apply relation, making sure the student ID is the same across the 2 relations, and gives us the name and major back. Now, if you remember your relational algebra, you can see clearly that this is a join of the student and apply relation. Actually a natural join, but we'll come to that in a moment. We're going to first rewrite it using the equivalent of the theta join operator, which is called inner join in SQL. And so this does the theta join, or the combination of student and apply, on a specific condition. So we'll change the where to on. And it is effectively the cross product of the 2 tables, but then when it does the cross product, it checks this condition and only keeps the tuples that satisfy the condition. So let's run that query, and of course we get the same result. The 2 queries we saw are exactly equivalent. We're just expressing them a little bit differently. Now, the inner join is the default join operator in SQL, so we can actually take away the word inner, and when we run that, we again get the same result because join is an abbreviation for inner join. Now let's see what happens when we have a join operator with additional conditions besides the one on the 2 tables. So this is also a query that we've seen before. This finds the name and GPA of students who came from a high school with less than 1,000 students. They've applied to major in computer science at Stanford. So we run the query and we find just 2 students in our result. So now let's rewrite that using the join operator. So we type join instead of comma, the comma being the cross product. And the join condition is, again, combining the student and apply records where the student ID matches, and the rest of this becomes our where condition. We go ahead and run the query, and we get the same result. Now, it turns out that we can actually put all of these conditions into our on clause. So we can make this where back into an and our on clause now is the and of all 3 conditions. We run the query, and we get the same result. Now you're probably thinking, how do I know what to put in the on clause and what to put in the where clause? Because these queries are obviously equivalent. Well, first of all, there are many equivalent queries in SQL. We can write things in different ways. In theory, a SQL query processor should execute them all in the most efficient possible way. But the join clause in particular is often used as a hint to the query processor on how to execute the query. So if we put all of these in the on condition, we're sort of saying as the query processor does the join, it should be applying all the conditions. When we make this a where, it's sort of a hint saying here's the condition that really applies to the combination of the tuples, and the rest of the conditions apply to separate attributes. Now let's take a look at what happens when we have three relations that we want to join. So this query is just finding a bunch of information about student application. So it's combining all three of our tables, and right here we're doing it with the comma, which is a cross product. It's combining tuples only when the student SID matches the apply SID and the apply CNAME matches the college CNAME. In other words, it's the same student who's that we're talking about in the apply relation, and we're capturing the same college as well. This is a typical query. From that, we're going to take the student ID, student name, GPA, the college name, and the enrollment. So common form of query, and here's the result. Now let's rewrite that query using the join operator. So we'll change our commas to joins, and we'll change our join condition, our where condition here to on, since these are the two conditions that are actually joining apply and student and joining apply with college. And we run the query, and as a matter of fact, we get an error. Now this query actually would run in a couple of the systems we've been using in this course. Right now I'm running the Postgres system because it actually supports the most of what I want to show today. But it does not support this particular three-way join, while MySQL and SQLite actually happen to do that. Postgres requires all join operators to be binary, explicitly just joining two relations. So we can change this query right here to be binary by joining apply and student first and then joining college. But we do need to be careful with our conditions, so we need to move the join condition for apply and student into this join here. So we've moved it in there, we take it away here, and here's the join condition for joining the result of this join with college, and we go ahead and run that, and now we get our result. Now I wanted to remark again briefly about the interaction between the expression of a query in SQL and the query processor. SQL systems do tend to actually follow the structure that is provided when we have join operators and we parenthesize them. So if we say first join apply and student and then join the result with college, typically that's exactly the order in which the query processor will do things. It doesn't have to do them in that order, and it can get the same result by doing them in a different order, but you might play around and you may discover that by changing the order that things are done in, or even just by moving the parentheses here, you'll get different performance out of the system. And again, people do use SQL to tune performance by changing the order around. Theoretically, that shouldn't happen because the system is supposed to find the best execution plan, but in practice, it does actually happen. Now let's move on to different types of joins. So let's go back to our first query where we use the inner join to combine the student and apply to find the majors that students applied to. So here's that query result. Now, obviously, this is in fact a natural join. So as a reminder from relational algebra, the natural join takes two relations that have column names in common, and then it performs a cross product that only keeps the tuples where the tuples have the same value in those common attribute names. So student and apply have the SID name in common, and so if I change this to the natural join, the system will automatically apply this equality between the student ID in the student relation and in the apply relation. So I can just simply take that condition away, and I run the query, and I get the same result. Now, the other thing that the natural join does automatically, aside from equating values in common attribute names, is it eliminates those duplicate attribute names in its result. So if I do a select star here from student natural join apply, I will see that there's only one column named SID in the result, rather than the column SID from the student and from the apply relation. Let's be even more explicit about that. Let's just take the SID column. And here we go, and there's just one SID column in the result. And if we tried to do the same thing without the natural join, if we were doing, for example, the cross product, then we would actually get an error because the column SID in the cross product of student apply is ambiguous. There's one from student and one from apply. But when we do the natural join, it's automatically equating those columns, and then we don't have to worry about ambiguity because the duplicate columns have been eliminated. Now let's take a look at the natural join with additional conditions. Let's go back to our query using the regular inner join that finds the name and GPA of students from a high school less than 1,000 who have applied to Stanford to major in CS. And here's those students. And we again have a join condition on attributes that have the same name. So we can just change this to the natural join of student and apply. And that allows us to eliminate the on condition. We run the query and we get the same result. Now there's a feature that goes along with the join operator in SQL that's considered actually better practice than using the natural join, and it's called the using clause. And the using clause explicitly lists the attributes that should be equated across the two relations. So we're going to take away the natural here. We're just going to use the regular inner join, but then we're going to specify that the student ID is the attribute that should be equated across student and apply. We can only put in the using clause any attributes that appear in both relations. It would be an error if we tried to use one that was in only one relation or the other. We'll run the query and we'll get the same result. The reason this is considered better practice, to make this explicit, is that because the natural join implicitly combines columns that have the same name, it's possible, say, to add a column to a relation that has the same name as the other relation, or not realize that two relations have the same column name, and the system will sort of underneath the covers equate those values, whereas when we put the attribute name in the query, we're saying explicitly that this attribute does mean the same thing across the two relations. And one thing I might add, by the way, in realistic applications, there can also often be 40, 50, even 100 attributes in a relation. So there's a higher chance that you really could have attributes that have the same name but aren't meant to be equated. And again, by putting explicitly the equated attributes in the column, it's just sort of in the query, it's just better software engineering practice. So most of my future examples are actually going to have using to express that natural join. Now let's take a look at using the join operator when we have more than one instance of the same relation. So this is actually a query we've seen in previous videos. It's combining two instances of the student relation in order to find pairs of students that have the same GPA. And in order to get each pair of students only once, we add the condition that the student ID on the left side is less than the one on the right side. Again, that's just to not have duplicates. So let's go ahead and run this query. And now let's try to convert this to using the join operator. So first of all, we see that we want to equate the GPAs. So we're going to make this a join where we use a using clause that tells us that we want the GPA on the left side relation to equal the GPA on the right side relation. And then we can take that condition out of our where clause, and then we can make the other part the on condition of our join. Let's go ahead and run that query, and we get an error. It turns out that most SQL systems, every one I've tried, doesn't allow you to have both a using clause and an on clause in combination with a join. You can have one or the other, but not both. So then we can just go ahead and take away the on, convert it to a where, and run the query, and we get the right answer. Let's do one more query that involves the self-join of student with itself, and this is just the natural join of two instances of student. So if you remember your relational algebra, it is a property that any relation joined with itself gives you back the original relation. So we'll run this query, and you can verify that this is, in fact, exactly equivalent to the student relation. In fact, why don't we just verify that ourselves? Let's just run select star from student. It actually changed the order of the result, but the result tuples are exactly the same. So we've seen the inner join, we've seen the natural join, we've seen the using clause. Now let's move to what I consider the most interesting part of the join family of operators, which is the outer join. We'll start with a query that's joining with the inner join, student and apply on the matching SID, and it's returning a few attributes, the student's name, ID, the college they're applying to, and the major. And here's the query. Now suppose that we also wanted in our result the information about students who haven't yet applied anywhere. And in our database, we actually have a couple of students who do not appear in the apply relation. If we're interested in adding those to our result, we do what's called the left outer join. Let's just go ahead and run that and see what we get. We get our same tuples as we had with the inner join, but we get, in addition, these tuples here that have blanks. Let me remind you, in this interface, blank is actually a null value. So this tuple here is Doris 456 null null. What the left outer join does is it takes any tuples on the left side of the join, so any tuples from the relation that's on the left, and if they don't have a matching tuple from the right, and that's called a dangling tuple, by the way. If there's a dangling tuple with no right matching tuple, it's still added to the result, and it's padded with null values. As with the inner join, we can actually abbreviate this. So when we have left, or as we'll see, right or full, we can take away the word outer, and that will implicitly do the left outer join. So we run this, and we get, again, the same result. Just an abbreviation. Now, we can also do a natural outer join. So we can do the natural left outer join. We could leave the word outer out. And that's the implicit version where we match the student IDs. Again, not that recommended from a software engineering standpoint, but it's worth seeing. And we will, again, get exactly the same result. Now, I should mention that everything we've seen so far with the join operators can be rewritten using regular SQL without join operators. And up until the outer join, that was probably very obvious. What we were doing was very similar to just doing your basic select from where with cross products and conditions. The outer join is slightly less obvious that you can do it in SQL, but you can. In fact, that's one of my favorite little SQL exercises, is to rewrite the outer join without using the outer join. And let's just go straight to the solution to that exercise for this particular query. And here it is. So what we do is we take the inner join, or in this case I've just done it in the cross product form. We take the inner join of student and apply, so all the tuples that actually match, and then we add to that result student tuples that don't have a matching tuple in apply, so where their student ID does not appear in the apply table. Okay, I hope you remember your subqueries in the where clause. And for those, we return the student name, the student ID, null and null. And we do the union of those two results, and that will give us exactly the same answer. And here it is. Now let's go back to our original query. In our query, we retained all student tuples, whether or not they matched an apply tuple. What if we wanted to do things the other way around? What if we wanted to retain apply tuples, whether or not they matched a student tuple? Well, you can probably guess that all we need to do is swap the order of apply and student and put apply on the left instead. It so happens our database actually doesn't have any apply tuples that don't match, so we'll add those tuples right now. We've added a student 321 applying to MIT for a couple of majors, and we don't have a matching 321 in our student table. So going back to the original query and swapping the order so that we keep all tuples of apply, whether or not they match, let's go ahead and run the query. And we take a look down here, and we see that we have those two applications of 321, even though there's no matching student name. Now, not surprisingly, SQL actually has a companion to the left outer join called the right outer join. So I don't actually have to swap my relations. I can actually use the right outer join with apply on the right-hand side. And what this says is we're going to find the student tuples that match the apply tuples. And then if there are tuples in apply that don't match the students, we'll add those padded with nulls. So here goes, and that's, again, the same result that we saw before with the two non-matching apply tuples and null values for the student name. Now, I'm sure what you're thinking is, what if we want to have unmatched tuples from both the left and the right appear in our result? And that's what's called the full outer join. So let's just change this right now to the full outer join. And let's move back to using the using clause, which I like better. That, and let's go ahead and run the query, and now we see that we have the unmatched apply tuples with null values for the name, and we also have the unmatched student tuples with null values for the college name and major. Not surprisingly, the full outer join can be expressed in other ways. We're going to start by expressing the full outer join using a combination of the left and right outer join. So here we go. Here we've got the left outer join where we're going to retain student tuples that don't match apply. We're going to do the right outer join where we retain apply tuples that don't match student, and then we're going to do the union of those. Now you might be thinking we're going to get a lot of duplicates because all the properly matching tuples are going to appear twice, once in the first one and once in the second. That is true, but remember the union operator automatically eliminates any duplicates. So we'll go ahead and run this query, and when we look at the result, we see that we get exactly the same result we got when we did the full outer join of the two relations. Now we can also simulate without using any join operators at all, which you probably figured out because we were able to simulate the left outer join. We already saw that. Here we go. This query has three parts. The first part finds all of the matching student and apply records. The second part adds to that those students who aren't present in apply, so it gives us their name and ID and the two null values for the attributes from the apply relation. And then the third part finds those apply records where there's not a matching student, and so it gives us the three attributes from apply, but then gives us a null for student name. So we go ahead and run this one, and we again get that you can verify we get the same result. The grand finale of this demonstration might seem a little esoteric, but it does demonstrate an interesting pitfall of the outer join. Let me start by reviewing for many of you the concepts of commutativity and associativity. Commutativity says when you do some operation A op B, that's always equivalent to B op A. And most operations, most of the join and the cross product and so on in SQL or relational algebra are commutative. One exception, of course, being the left outer join or the right outer join. Associativity says when you have these binary operations, you can do them in either order first. In other words, you could first do the operation on A and B and then combine the result with C, or you could first do the operation on B and C and then combine the result with A, even if you're doing the same left to right order. Associativity is also very common. The cross product and the natural join and so on are associative. What's interesting is the outer join is not associative. And I'm going to demonstrate that not with the college database, but with a very simple set of tables, each with one tuple that I'm going to set up specifically to make my point. So I'm going to create three tables, each with two attributes, and put just one tuple in each one. So we've got table T1 with attributes A and B and tuple 1, 2. We've got T2 with attributes B and C and a tuple 2, 3 that matches the T1 tuple. And then table T3 has attributes A and C, so attribute A from table T1, or matching T1, and C from T2, but the values don't match at all. I would highly recommend you pull out a pencil and paper and actually just write these tables and tuples down so you can see what's happening. Now let's look at this question of associativity. So we're going to do the natural full outer join of the three tables, and we're going to start by putting the parentheses on the left. So we're first going to do the outer join of T1 and T2, and then do the outer join of that result with T3. And let's run the query, and we see that we got two tuples, 1, 2, 3, and 4 null 5. We got 1, 2, 3 because T1 and T2 had that nice pair of tuples that combined with each other, but then when we took that result and did the outer join with T3, that gave us an unmatching tuple in T3, so we got 4 and 5 with a null value in the B. Now let's try the other associativity. Let's just change our parentheses so that T2 is outer joined with T3 first, and then the result of that is outer joined with T1. We run the query and we get a different result. And that's because we started with our unmatching tuples, which then didn't match correctly with T1. Again, the best way to do this is to take your pencil and paper and look at what's happening, or try running the queries yourself to see that the outer join is not associative. And by the way, the left outer join and right outer join are not associative either. So none of the outer joins are associative. The full outer join, however, is commutative, while the others aren't. Okay, so why is this important? It's important because if you do queries that do have outer joins of more than one relation, then it is important to think about the order. It's not a performance thing. It's actually what result you get may be different with different orders and parenthesizations of your outer joins. So in conclusion, the family of join operators is used in SQL to combine relations where we're explicitly doing operations like relational algebra. The inner join is the relational algebra theta join, where we explicitly combine relations on a specific condition. We have the natural join operation, which implicitly equates the values in columns that have the same name and eliminates those duplicate columns. Both of those can be expressed in fairly similar ways without the join operator. The outer join, however, is sort of significantly different because it does add the tuples that don't match the join condition and pads them with null values, and it's quite useful. People use join operators quite a lot. The one thing I mentioned is that join operators can be used to kind of tell the query processor how it should execute the query, and that can sometimes be used to improve the performance of queries, of equivalent queries, though in theory, again, database systems should always find the best way to execute their queries, but that's a tough thing to do, and so people do sometimes give hints in the way they formulate their queries, sometimes using the join family of operators to do that.